Good morning, friends. Indeed, I feel extremely happy to be here again for my course Engineering Thermodynamics. As of now, I have completed my module 1, which consists of properties of thermodynamics, properties of substances, zeroth law of thermodynamics, heat, work, different processes, and so many things I have already covered. In my last class, I have just introduced about the second law of thermodynamics, and today I will further go for some statement of second law of thermodynamics. Actually, the second law of thermodynamics is nothing but it is a law of conservation of energy. It means the energy cannot be created, cannot be destroyed. It can be transferred from one form of energy to another form of energy. So that we have seen in our my previous lecture. Today I am going to take two special statements, and then we will see that how this second law of thermodynamics is going on. So here we have the second law of thermodynamics. I will further elaborate. Then we have the Kelvin-Planck statement, then Clausius statement. So these two statements along with some new topics we are going to discuss today in this lecture. So if you see here, we have in the previous lecture we have discussed about heat engine, then heat pump, then efficiency of the heat pump, heat engine, and the COP of the heat pump or the refrigerator. Now I will go for the need of second law of thermodynamics. So in this I will be observing that why we required the second law of thermodynamics. Okay, so we can see that following are the primary need for the second law of thermodynamics. First one is to ascertain permissible direction of the work and energy flow, to compare different thermodynamic cycles, fix up condition for the equilibrium, to ascertain temperature scale independent of the thermodynamic substances. Absolute temperature was established by second law of thermodynamics. So that is also the need. By the second law of thermodynamics only we have got the absolute temperature. Till that time we have a relative temperature we used to have, like 0 degree centigrade. So just 0 degree centigrade, in fact it is not absolute zero. So this absolute zero we have found by the help of second law of the thermodynamics, and this credit goes to the mass Kelvin. To quantify the thermodynamic properties like internal energy U, the enthalpy H, and that are not directly measurable, 0.1 to 5 for classical thermodynamics. So here if you see that these are the classical thermodynamics. The last point is the 6th number is the modern thermodynamics, that is the beyond classical thermodynamics, like entropy is used in thermodynamics, and also for information flow, data flow, exchange of information, etc. So here we can see I have divided this thing into two groups, 1 to 5. They are in the classical thermodynamics. In this, first one is to ascertain permissible direction of your work and energy flow. In which direction it is possible. That is possibility. Means if I am rubbing like this, I am putting my work in my hand, I am getting some heat. I am getting heat in my palm, but if I put the same heat again, my hand will not move like this. It means only one direction is possible. Means if I am putting some work, I am giving some work, due to the friction, this heat is generated. Okay, so but this generation of the heat, if I am putting here, my hand will not move. So that is the limitations. So this type of limitations are provided by the help of the second law of thermodynamics. Next is to compare different thermodynamic cycles. We will be learning that Otto cycle, diesel cycle, Carnot cycle, Ericsson cycle. There are so many other cycles, and we can compare by the help of the second law of thermodynamics. Fix up the condition for equilibrium. We can also fix the condition at what condition there will be no flow of energy. Energy will remain in the same condition. So that also we can fix up by this second law of thermodynamics. To a certain temperature scale depend of the thermodynamic substances, and by the help of this we have find out the absolute temperature that I am going to discuss in the next slide in detail. To quantify the thermodynamic properties like internal energy U, enthalpy H, that are not directly measurable. These are not directly measurable. You remember that we have find out the some properties before also. In our first law of thermodynamics, we have got some properties like internal energy and some other properties that we can find out by this. But the sixth point is it is not a classical. It can be used in computer science. It can be used for information technology. It can be used for the human nature, in biology, all the field. This entropy is visible. Entropy is nothing but it is a chaos. Means if you are putting 100 unit of work, 100 unit of heat you will not get. Or if you put the 100 unit of heat, you will not get 100 unit of work. So how much you can get? There is a limitations. So this loss of energy is a natural phenomena. And that is a chaos in the life. In every human life also, we have a lot of problems. We are intending that we will do everything good, but nothing will happen. This type of situation is called the entropy. This I will be discussing in my due course of time. So now I will discuss about second law of thermodynamics and introduction. So here we can see the second law of thermodynamics is a physical law based on universal experience concerning heat and energy interconversion. So heat and the energy, this can be converted to work on some other type of things. So how the heat and energy can be converted from one form to another and from another form to this form. Next is one simple statement of the law is that heat always moves from hotter object to colder object or downhill unless energy is supplied to reverse the direction of heat flow. As per the natural phenomena, if you see that if outside of your room the atmosphere is very hot during summer, the hot will come to the inside. Same way, in the winter season, if your outside is cool, your room will also get cool. So we need some additional energy to make the room hot. We have to put the heater. We have to put some hot arrangement. Same way, in the summer, we need the air conditioner and other things to make sure that our room is cool. So these things are not possible. It is not a natural or spontaneous thing. From low temperature to high temperature, if you want to go, you need some additional work. Additional energy has to be given. Then only it is possible. This is given by the second law of thermodynamics, which is not stated by the first law of thermodynamics. Another definition is not all heat energy can be converted into work in a cyclic process. If the process is cyclic, means it is moving from one point to another point to third point, fourth point, again it is reaching to the original point. Every heat cannot be converted to the work. Means there, if I am supplying 100 kilojoule of heat so that I can get the work of 100 kilojoule, it is not possible. because some part is lost due to friction, due to some other chaotic situation, not ideal condition. So this, not all heat energy can be converted into work in a cyclic process. Establishes the concept of entropy by the help of the second law of thermodynamics. A new term is going to be introduced that is called the entropy as a physical property of a thermodynamic system. This entropy we normally represent by S. I am going to discuss in detail about entropy in my next lectures. We will be doing some numericals and other things, and hope this will be very useful. And entropy, just now I discussed, it is a non-ideal situation in which some losses will happen whatever you do. Then we have it can be used to predict whether processes are forbidden despite obeying the requirement of conservation of energy. Means it is obeying the law, first law of thermodynamics, that is a conservation of energy, but whether it is possible or not, this is given by this second law of thermodynamics. Provides necessary criteria for spontaneous processes. Spontaneous processes are the processes which happens naturally. Like if I rub like this, heat will be generated. But if I put the heat, my hand may not move. That's so that another is not spontaneous. Or if this room is having 40 degrees centigrade and outside is 20 degrees centigrade, this heat from the room will go to the lower side. That is a spontaneous process. But from the outside where the temperature is low and you want to make this room hot, it is not possible. This is only possible if you give some additional energy for this. Now I am going to discuss about statement of second law of thermodynamics. I will start with some historical perspective, how these things was developed and who are the responsible for development of the second law of thermodynamics. Because history also we should understand for each and every time, so that we should remember that how the things have come out. It is not just like that. Everything has taken a lot of pain, lot of work has been done to get that laws. So main statements, first one is the Rudolf Clausius, 1854. He has given the statement. And then the second person is Lord Kelvin in 1851. These two statements are very, very popular. There are so many other statements, but as for thermodynamics, classical thermodynamics is concerned, we will be discussing about these two statements of second law of thermodynamics. So axiomatic thermodynamics by Constantin Carathéodory, 1909, another statement. These statements cast the law in general physical term, citing the impossibility of a certain process. So these three laws, they are giving the direction that which one is possible and which one is not possible. Everything is not possible. Like we have so much water in ocean. We have a lot of air in atmosphere. This air contains huge amount of energy, but how much we can use it? We have huge amount of energy in the ocean, trillions of kilojoules. But how much we can use? If we are able to use the whole energy, we can do everything without any much problem. So this gives some limitations. The Clausius and the Kelvin statements have been shown to be the equivalent. Both are mostly same. Now I will discuss about Clausius statement of second law of thermodynamics. So here you can see that. So here we have Clausius statement of second law of thermodynamics. So The name of this Clausius is a German scientist. His name is Rudolf Clausius. Laid the foundation for the second law of thermodynamics in 1850 by examining the relation between heat transfer and the work. So he has given the statement. His formulation of the second law, which was published in German in 1854, is known as the Clausius statement. This is his statement, that is called the Clausius statement. Heat can never pass from a colder to a warmer body without some other change connected therewith, occurring at the same time. So in that time, he has given like this statement, which is shown that heat can never be passed from a colder to a warmer body. If anything is cold, here is a hot. So from cold to hot, the passing of energy is not possible till the time we are not able to have some changes connected therewith, occurring at the same time. So this we have to see it, that we can do like that. So heat cannot spontaneously flow from cold region to hot region without external work being performed on the system. So the statement which is given before, that heat can never pass from a colder to warmer body, the another statement of the same way is heat cannot spontaneously flow. Spontaneous means natural. From a cold region to hot region without external work being performed on the system. So if you want the heat should flow from cold to hot, we need some work to be done there. Some external work has to be performed, so that then only it is possible. Like you want to make your room cool. It is not possible. So we have to give electricity and we have to operate the compressors, condenser and all, and those things will extract the heat and they will discharge the heat in the higher temperature than the room. So this statement is given by Clausius, Rudolf Clausius, and this statement says that if anything spontaneous flow from cold body to hot body is not possible without expending some external work, which is evident from ordinary experience of the refrigeration. We have seen that how we are operating the refrigerator in our home. We want to make the inside the refrigerator very cool, so that all the eatables and other materials are kept for a long time. So this is not possible without expending the electrical energy which we have to supply. Example, in a refrigerator, heat is transferred from cold to hot, but only when forced by an external agent, the refrigeration system. So this is possible only because some refrigerants are there. These refrigerants are evaporating and they are extracting the heat inside the chamber, and they are taken out from the refrigerator, and in this way the refrigerator is cooled. Now the second very important statement is Kelvin-Planck statement. This is about the engine, and the Kelvin, that previous one is Clausius, it is for the refrigerator and the heat pump. So the statement says about it is impossible to construct a device that operates in a cyclic process and produces no effect other than raising of a weight and exchange of heat with a single reservoir. Very, very important. I have given here superscript 1, superscript 2, then here we have the raising of a weight and the single reservoir. Here we have to see very philosophical way. It is not just word by word. If you go the word by word, it is not, you cannot understand the things. So it is impossible. First thing, the word has come impossible. Everybody will feel that what a negative thought. The Kelvin-Planck has started his statement by the impossible, so that we will not try the impossible thing. We will not go for wasting of time. So he has put very, very important word, that is impossible. Don't attempt such activities. To construct a device, which kind of device you can make? It should be device operating in a cyclic process. So the device which is operating in a cyclic process and produces no effect other than raising of a weight. Here the meaning raising of a weight, it doesn't mean if you take this and you are lifting the weight like this. It is not the meaning. Here it is a philosophical way. Raising of weight means you are working against the nature. You are working against the resistance. Your whole thermodynamics work is not the same as in the normal physics, that if you move any object from one place to another place, the force which you are applying and the distance, displacement, it is moved. Force into displacement is a work. But here in thermodynamics, force into displacement is not the work. Force should be the resistance force, not the normal force. Means if this is your object and you are putting like this, there should be some resistance, the friction force. Against this you are working. So that force is required. That force into the distance, how much it is traveled. So raising of weight means, it means doing of work against a resistance. Means like raising of weight means against the gravity. You are making the work in such a way that you are lifting this thing. Means you are against the gravity. So gravity is the resistance. So if your object is going from bottom to top, then only work will be done. And if you leave from here to here, work will not be done for the thermodynamic point of view. But if you see, if you are leaving like this also, normal work is done. As for physics, the force into distance, how much it is traveled, that much work you have done. But in thermodynamics, if it is no resistance, no work. That is the importance of the thermodynamics. Raising of the weight and exchange of heat with a single reservoir. That is also not possible. If you are only one heat rejection point is there, you are extracting and you are putting in the same place, it will not work. This means there is no heat sink in a system. So QL is equal to 0. This means rejection of heat is needed. Then only work will be produced. So if you see here that you have this is the source, and you are taking heat from here, you are using it and you are rejecting here. This type of system is not possible. This is not possible. This has to be high temperature and this should be low temperature. So this has to move in this direction. Then only work will be performed. So two reservoir is required. The single reservoir, if you are using, it is not possible. Don't undertake any such type of project where you are taking the heat from there and you are not rejecting the heat. Heat has to be rejected. Then only you will get the work. So in this situation, this also gives about the efficiency, the heat engine. It is the efficiency of the heat engine. This is N is equal to 1 minus QL by QH. So this is the QH, and here if you have one engine and this is the QL. So the efficiency of engine is equal to eta is equal to 1 minus QL by QH. This should be always less than 1 or less than 100%. If you make this QL, means this is not there, the sink is not there, so this will be 0 here, so eta will be 100%. This is not possible. If anywhere you are getting 100% efficiency, you should feel that you are doing some mistake. It is not possible. Our objective is to reach to the 100%, but as per the second law of thermodynamics or the Kelvin-Planck statement, it says that the heat engine efficiency will always remain less than 1 or less than 100%. So the efficiency of the heat engine will always be less than 100%. So that is the Kelvin-Planck statement. So now I am going ahead. So TH will be always greater than TL. So this is the TH, this is high, and this is the TL, low. This is called the sink, and this is called the source. This will move like this. Here is the engine, this is the QL. So this TH will be greater than TL. Then only it is possible. TH is a heat source temperature, TL is a heat sink temperature. So here the KP statement of the second law of relates to the heat engine, but we also have some devices which transfer heat from low to high temperature zone, like heat pump to heat the room in winter, and refrigerator or air conditioner to cool the environment. We will discuss next statement called the Clausius statement. So this I have already discussed, but I am again new way I am here discussing. This is the again it is impossible to construct a device that operates in a cyclic and produces no effect other than effective transfer of heat. In that, this device here, it was raising of the weight. Effective here. This effective transfer of heat. So means here heat transfer is taking place. In the KP or Kelvin-Planck statement, it is for the engine, but this is for the refrigerator and the heat pump. So here effective heat transfer from low temperature body to a high temperature body is not possible. So that is the statement of the Clausius statement. This statement talk about heat pump and the refrigerator. Here heat will transfer from TL low temperature to high temperature without expending work on it. That is W in. And so W is greater than 0. So now here, if it is greater than 0, then coefficient of performance will be less than infinity if W is equal to 0. Heat cannot be transferred from low to high temperature without a work device. Then from work device to TH, each device should have a temperature difference. So this you can see in this diagram. Here is the sink. Here is the source. If you want to transfer this heat from here to high temperature, you need a work device where we have to put this work in. We are giving the work in, and this device is rotating, and from here heat is transferred from here to here. So next question is why we need the two statement. For the same law, there is one law, that is the second law of thermodynamics. Here we have the two statement. Even we have so many other statement, but here I am discussing about two because they are the very important and very initially they were developed. So here we have the two statement. One is the KP and another is the Clausius. This Clausius statement is for the refrigerator or heat pump. Heat pump. And this is for the heat engine. Okay, so this will used to do the work, and this is used to transfer of heat. That is effective heat transfer. It is mentioned here. This is used for this purpose. So two statements are made for different applications. That is why here we are studying the two statement. Now we have to see that how this equivalence, both are equivalence or not. Kelvin-Planck and the Clausius statements are equivalent or not. So here we can see that let us say for heat engine, for Kp statement, that is the blue line. If you see here, heat engine means it is TH, the source is having high temperature, sink is having low temperature. From here, the QH is discharging from here, work is out. Here it is QL, which is less than 0, and here it is going. Now we are extracting from here, it is a Clausius and it is a Kelvin-Planck. So here we are extracting the QL from here. Here is the heat pump. Here W in, which is greater than 0. And here we are putting this thing. Okay, so we are taking this heat from here and we are supplying some part here. So let us imagine another device, that is heat pump or the refrigerator, as a green line. This one, here is a refrigerator and here is the engine. This is the engine. So now take heat engine and the heat pump as one with a red dotted line. This you can see here. We have made a red dotted line here. Here we can see that this Q dot H is equal to, this Q dot H is equal to QH minus QL. Okay. So this Q dot H is equal to QH minus QL, and W dot is equal to W net, which is QH minus QL. So now, so net Q prime is equal to QH prime minus W dot is equal to 0. No heat is released, so violation of Kp statement. So here it is not possible because we are not releasing any heat. We are releasing here and we are extracting from this thing. Again, it is going in the same place. This type of machine is not possible. So it is violation of Clausius statement leads to automatic violation of Kelvin-Planck statement and vice versa. So in this way, we can prove that both are equivalent. Kelvin, Planck and the Clausius, both statements are equivalent, and you can change from Kp statement to the Clausius and from Clausius to the Kp statement. Next topic, I am going to discuss about corollaries of second law of thermodynamics, perpetual motion machine of second kind, Maxwell-Demons, reversible processes, irreversible processes, factors affecting irreversibility. So in my next class, I am going to discuss about these topics, and these will be very interesting. These are my references which I am taking from PK Knob, Engineering Thermodynamics, Tata McGraw-Hill's 4th edition, 2008, Eunice Sengel, Michael A. Ball's Thermodynamics and Engineering Approach, Tata McGraw-Hill's 7th edition, 2011. Also, I am referring some IIT Kanpur NPTEL by Professor D.P. Mishra, which is mentioned here. Any questions you are welcome to ask. You can approach me in my email, that is ydwivedi@gmail.com. This is my email which you can call me. Hope you have understood. Please subscribe and like, which is like button. You can press it. That will be enhancing my, if any improvement is needed, I will try to improve. Thank you very much, and hope this will be very useful for you all. And very soon I am going for the next lecture. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.